everyone.
Yeah.
Welcome at the Innovation Café, also for the people watching at home. For the people that are here for the first time, and see, I think, some new faces as well here. We are a networking event here in Eindhoven, where we also show what Eindhoven has to offer in the fields of tech and design. And we do this by always organizing a talk. Today this is being presented by Marco Arts from Carbyon.
Carbyon.
Yeah. There you go. So he will talk a little bit about what they do and where they're going.
Yeah.
I want to invite you all to our next events. We're here every Thursday, every week the same time. And you can look at our program on ehvinnovationcafe.org. So we hope to see you again another time, also for the people at home, of course. If you want to rewatch old talks, everything is also on the website, so feel free to browse around, and I'll see you after.
Thank you, Marco. It was actually quite funny when I came in here. I've been involved in the Eindhoven Innovation Cafe before we even knew that COVID would come. And actually my participation in the Carbyon actually sort of started here. There was someone present from the High-Tech Excel organization. That's an incubator here at the High-Tech campus in Eindhoven. And they are organizing every now and then, they organize their famous hackathons around technology and possible solutions that can be achieved by this technology. And she said, oh, you have to come over, why don't you join this hackathon? And actually at that hackathon, Carbyon was born. So that's pretty nice story linking to this place. My name is Marco Arts. I work for Carbyon, that's how we pronounce it. And I'm going to talk about, you're not seeing anything now, but you should see my first slide. There it goes. I'm going to talk about next generation carbon removal. That's a mouthful, and I will explain, of course, what it is. I can talk hours about that. I'm not a family of Fidel Castro, but I could. I'm not going to bore you with that. What I did is I prepared, I think it's 5 or 6 slides, through which I would like to talk you through what is carbon removal, why is it important anyway, how does it work, how does our solution work, why is it unique, and where are we going. And I think I need roughly 10 to 15 minutes for that. So I would also like to have some room for questions or feedback from your side. I would really welcome that, because that's always good to have. So carbon removal, you probably understand it has to do with climate change, which is one of the biggest problems of our time. And in order to counter climate change, we need carbon removal, and I'll explain why. But first we have to know, I'll do this very shortly because I think it's well known to most of you. How did this start? Because we, since the Industrial Revolution, we emitted enormous amounts of CO2 into our atmosphere. And this CO2 concentration has risen by 50% since then. And there's a correlation between global warming and this high CO2 concentration. I don't think that's anything new for you. And I think most countries, or many countries at least, are now making plans to become what they call net neutral, or to go to net zero emissions by 2050. Now what does that mean, net zero emissions? I sometimes make the comparison with a bathtub, being our atmosphere, which is filled with water, being CO2. And the tap is still open because there's still coming more water, CO2, into the bathtub. Actually, year over year, this is still growing. And now we say, okay, by 2050, the level of the water in the bathtub will not rise any further. That would be nice. But that's a huge challenge, because we are not able to fully close the tap. So there will still be, at least be dripping, but I think a bit more of CO2 into our atmosphere. And that has to do with the fact that we cannot, by that time, replace all our energy sources, all our materials, to become really fully renewable. So we need another mechanism to make sure that the water level will not rise. What about pulling the plug of the bath? So letting out water. In the metaphor, removing carbon dioxide from the atmosphere. That's what carbon removal is about, and it's also sometimes called a net negative solution or a net negative technology. Now that sounds very easy, but it is actually really difficult. There's one species on Earth which is extremely good in this, and that's plants and trees. And that's indeed one of the solutions that we should look after. And there are various other solutions to take care of carbon removal from the atmosphere. And if you want, I can elaborate on that. I have a slide on that, but I won't do that now. But what I want to say is that all of these solutions have pros and cons, and there is no silver bullet. So none of them will be enough to solve this whole problem. So we probably need them all, because the challenge is that big. And one of the solutions, that's a technology solution, is what is called direct air capture, and that means nothing more or less than capturing CO2 directly out of ambient air. These are machines doing this, and they already exist. 2 weeks ago, our Swiss colleagues called Kleinworks, they launched the biggest plant, direct air capture plant in Iceland. And what they do is they capture the CO2 out of the air there, and they store it underground in mineral rocks. And there it will stay permanently. That's direct air capture. There is one big problem with direct air capture, is that it's way too expensive at this moment. It is roughly 500 euro to catch 1 ton of CO2. And you've seen this big number, that's the range of tons that we actually have to capture in the next century or so. So we have to bring down the costs, and the costs are so high because it takes a lot of energy to capture CO2 out of air. And if you see images of the installations that are currently being deployed, they are really huge, so they require a lot of capital. And we at Carbyon, we are heading for a solution for that. So we are targeting to lower these costs. And I will explain very shortly, because it's quite a technical subject, how our machine works and why it is different than currently available state-of-the-art. In the basics, it is of course this. Our machine takes in air and as its output CO2. And it works actually in a two-way process. There is one part of the process is where we take in the air, where we capture air into the machine, and the CO2 is actually captured on a material. I will explain in a minute what that is. And in the second step, the CO2 needs to be released again, because otherwise it would stay in the material, and we want to release it for further processing. Now this capturing and releasing is done by a thin film material. That's a material, I just spoke someone from TNO sitting here in the front. It's a material that has been developed by TNO, which was initially intended for usage in solar panels. But actually by accident, our founder, he worked at TNO at that moment, he discovered that it could also be used to capture CO2. And why is this material so special? It has some very favorable characteristics to do this, to bring down the energy costs. One of them is that it has a very high internal surface area. You can compare it a little bit with the inside of your intestines. They have 1 square centimeter is like 100 square centimeter of surface. And this material does that way better. It has 1 square meter of that material has an internal surface area of more than 100,000 square meters. And on that entire surface we can modify it, and on all that surface the CO2 can be captured. What's more, it has a very low pressure drop. That's a bit of a strange term, but it means actually when you blow air through it, that costs very little energy because it's very porous. And therefore it also captures CO2 very fast, and it can be released by heating up the material to 60 or 80 degrees maximum. And that means it actually requires relatively low energy. But that's the basics, that's the material that we're talking about. We also have to think about how we can actually implement this process into a working machine. And we developed a unique machine design which is based around a rotating drum. And I'm not exactly sure what the button for the laser pointer was, but the green area, the green circle, is a drum on which the thin film material is attached. And that rotates from the air chamber where the air is blown through and the CO2 is captured to the red area, and that's what we call the CO2 chamber. And there the material is heated up and the CO2 is released. And then it repeats. So it's a continuous process. And that goes quite fast. Now the trick here is that the blue spots marking the separation between the blue and the red chamber. We have to make sure that there is no mixing of gases. So in the air chamber, we don't want any CO2, and in the CO2 chamber, we don't want any air, because otherwise we're doing this for nothing, basically. And that's a technique that we have developed together with high-tech manufacturing industry, actually here in Eindhoven. That's also one of the reasons why we are here in this region, because this is one of the few regions where this high precision mechatronics can be developed. And out of that, we can make a machine that can be mass manufactured, and thereby we can also lower the costs. And in our models, and of course we have to prove that, we have a target, and we think we can still make that, of 50 euro per ton. That's 1/10 of the current capturing price. And now why is that price important? It is important because carbon has a value. And that's not really strange, because all the carbon that we use for energy, for materials, we currently take mostly from fossil sources. And of course we pay for that. So if we can take this carbon not from out of the ground, but from the air, of course it has a value, but it is renewable. And basically with the CO2 that we capture, we can do two things. You can actually use it, or we could also say recycle it, because we have already used it once, to make, for example, fuels, but renewable fuels. Why is that a good thing? Because, for example, airplanes, they fly on kerosene, fossil kerosene at this moment. And they will probably not be able, at least for long distance flight, not be able to fly on batteries or on hydrogen for the next decades to come. Okay, you could say, then we better stop flying. It's a good idea, that's the best idea actually, climate-wise. But I don't think that will happen. So we have to find a way also to make flying climate neutral. And that can be done with making renewable fuels. So renewable CO2 together with green hydrogen can make renewable fuels. That's a well-known process actually. Same goes for materials that are currently sourced from fossil sources, but also food, for example, carbonated drinks need CO2. And also greenhouses actually use CO2, currently fossil CO2, to raise the level of CO2 in greenhouses to improve crop growth. And that's not a very sustainable thing to do. That's one part, that's usage. That's actually is part of closing the tap in the bathtub metaphor. The pulling the plug is storage. So that's actually really pulling the CO2 out of the air and stowing it away forever. That's storage or removal. And we can store it away underground or under seas in empty gas fields or empty mine fields, but also in minerals. And actually we are then putting it back where it came from, because it came out of fossil sources that were that developed there over billions of years. And that's what we call net negative. This is this pulling the plug. A little bit on who we are, and then I will tell you where we are heading. As I told you, we started here in Eindhoven. We're still located in Eindhoven. We're a spin-off of TNO, where the core technology actually was developed. And we now have a team of 11 FTEs, let's say a heavy science and engineering team, because that's the phase we are in. But we still have the shared dream together to tackle climate change, and that's also what really binds us. But we always say, yeah, that's the Carbyon team, but the Carbyon team is actually much bigger. We really make use of the ecosystem in this region in terms of research institutes and academics. So that's TNO, but also DIFR, that's a Fundamental Energy Research Institute here in Eindhoven, and of course universities in this area. But also of corporates, mainly high-tech manufacturing. There's really unique knowledge and tools in this area that we really helpfully use. For example, from ASML, Philips, and also VDL. And that combination is for us really a reason to start in this region, but also to stay in this region. Where are we heading? We are now we're actually finalizing our proven principles. How it's called is actually all the measurements that we have to do on this thin film material, but also making sure that on the machine side, specifically these gas seals actually work good enough. That's what we're finalizing now, and we're now in a funding round to get the resources to make an integrated prototype. So actually to bring these two elements together and really make a working machine that takes in air and outputs CO2. And then we want to do pilots with several customers. I've got a new suggestion just at the entrance here. Thank you for that. And we want to actually have our first machine on the market in 2024. And from there on, we have to grow really fast, because if we really want to have an impact on climate change, we have to go to what we call the Gigaton scale level. That means that we are able to capture gigatons of CO2. That will not be next year, I can tell you, but we're aiming for that in the 2030s. And in that way, we can contribute to climate, mitigating climate change, but also make sure that we finally, actually end the fossil era, because that's still the tap that remains open, and we have to close it. But also the storage part, these 1,600 teratons, the number that I started with, are historical emissions that we also have to get rid of in some way. Maybe not all of them, but if we levelize the bathtub right now, it will be enough, that's the calculations of science, to stay within the 1.5 degree temperature rise. But effects on climate and ecosystems will linger on for at least 200 to 300 years if we stay on that level. So we actually need to lower the concentration of CO2 in the atmosphere. And that's a huge challenge, that we really need tens and hundreds of gigatons to be captured on a yearly basis. That's immense. People also ask us, okay, how are you going to do that? A gigaton of CO2, that's a lot, because it's a gas, it doesn't weigh anything or very little, so a gigaton is a huge volume. And we made a calculation. What does it mean? We are producing 100 ton per year capacity units, and we would need 600,000 roughly of these to be installed for this capacity. And then people say, yeah, that's really a lot, 600,000 of these machines for 1 gigaton. How are you going to do that? Okay, it is a lot, I have to admit, but it's by far impossible. If you compare it to a small size automotive manufacturer, they are doing these numbers. If humanity is good in anything, then it's really scaling up mass production. That's something we learned specifically during and after the Second World War. So we believe that's possible. That's actually my last slide. I have my contact details here. Ready to answer any questions, also from the people at home or at office. I want you to remember a few things. That in order to counter climate change, we need carbon removal. I think that's important to realize. There are various solutions for that. That's good news. They're all needed. direct air capture is one of them. It's a technology. And here in this region, we have everything in place to make that happen, because the technology and the tools that we are using, they have matured in the semiconductor industry, ASML, Philips, VDL, whatever. And now we can use them to tackle one of the biggest challenges of our time. Thank you very much, and I'm happy to answer any question. Thank you. Yes.
If you can repeat it for the audio, that would be great. You mentioned that that is for now in 2024 you want the first commercial tool to be ready. Have you also already are you also in contact already with like government and stuff like that to see if this is possible to make it more available instead of making it a commercial product?
Yes, of course we are, and that's not easy. Oh yeah, sorry. Sorry, I will repeat the question. The question is, by 2024, I had it on my slide, we want to have the first commercial product on the market. And Marco is asking if we are also talking to governments, so that we don't have to go, let's say, only the commercial route, but also the government route to get going. One remark before I start answering these questions, Carbyon would not have existed without government support. So our first funding actually came from the province of Noord-Brabant, and without that we would not have existed. So let's not assume that governments are not doing anything, which is basically the case for most of our funding at this moment. But yes, there are two factors. It is a societal problem in a way, because I sometimes say, okay, this removal of all these gigatons that we need to do is basically cleaning up our own shit. That's how I boldly call it. But at this moment there are no policies or regulations to take care of that. The thing is, the fact that it's called an economic externality, the fact that companies and consumers have been able to emit these enormous amounts of CO2, they have been able to do that without a cost, without a penalty. It didn't have a price to pump CO2 into the air. There are regulations are being made now, and tax incentives are coming up to change that. Basically, just in a way how we did it, at least here in this part of Europe, I think I must say, to clean our water. 150 years ago, drinking water here was also heavily polluted, and we decided, okay, we're going to put a tax on polluting water, and we're going to use that money to clean it up and make sure that it remains clean. And these kind of policies are now being made. One of them is that in the EU there is a trading system for CO2 emissions. It's called ETS. And the funny thing is actually that the price in the trading system for 1 ton of CO2 is actually touching €60 already. And it's probably going up, are the expectations. And we will see that both corporates but also consumers will be taxed by the amount of CO2 that they actually emit at a certain price. So these are regulations that will come. That will take time because it will cost money. But that will come for sure. Also in the US, the Biden administration is quite aggressively changing plans now compared to the previous administration. That's not surprising, I think, but there are things happening, but that will take time. But it will come for sure, yeah. But in the meanwhile, we are also, we are not a government organization, so we also have to survive. And of course, profit is not our main goal. That's it's a means to make sure that we can have maximum impact. And to scale up this is going to be it's going to cost a lot of money and resources. So we probably can't do this without government support. Yeah. Thank you. Any more questions?
Yeah, I have
Yeah.
a question because you mentioned that it's a continuous process.
Yeah.
So I was wondering, are you thinking about storing the CO2 or maybe making like a pipeline to somebody that's uses CO2?
Okay, it's a good question. Shall I repeat it again? Okay, question is, we have a continuous process which is really different from existing processes. And of course, there's continuous output of CO2. And where do you go with the CO2? That's a good question. Depends on the application. So starting maybe with the storage, if you store it, then the easiest thing to do is, for example, if you store it in an empty gas field under the North Sea, then we place our equipment at the Maasvlakte, that's close to the sea, to the North Sea near Rotterdam, because there is the pipeline that directly goes into the bottom of the North Sea. So we can continuously pump CO2 in there. That's, by the way, a big advantage of direct air capture. It can be captured anywhere in the world. So where there's existing infrastructure, you can put machines there. Similar thing goes for if we want to make renewable kerosene. For example, Shell is currently making kerosene in Qatar. All the infrastructure is there. That's an ideal location for us to put our equipment to capture CO2. It's an ideal location to make renewable hydrogen because you have cheap electricity, the sun is shining all day long, and you can connect to the existing infrastructure. So that's also a continuous output process. But you can also store it temporarily, so you can put it under pressure. That's possible. But for example, and then it goes into bottles or in other containers. For example, in greenhouses, it's directly used. So it's captured and it's pumped into the greenhouse. So that's also a different application. Yeah?
But is this something that you're also focusing on? Or
No, we're not focusing on... Yeah. Question is if we are also focusing on this post-processing. No, we're not doing that. We're not good at that. We're not planning to be any good at that. Others are really mature in doing that, so we are not going to develop that. So we purely focus on how can we get CO2 out of ambient air as cheaply as possible, and how can we scale that up as fast as possible. Yeah.
Okay.
Albert.
It was just an extension on the question of storing it, because you mentioned underground. Yesterday I saw a documentary which was about hydrogen, and they want to store that underground as well as places to store it. Will that not be a conflict? Because hydrogen, one of the alternatives to, because that was like a hybrid engine,
Yeah.
which hydrogen was used to generate electricity, and
Yeah.
that you could power like trucks and everything more sustainably and for longer periods than just pure electricity would. But they also wanted to make use of the gas pipeline infrastructure. Will that not be competing, or are there enough pockets?
Yeah, I would not suggest to store them both in the same area. I'm not a chemist, but I don't think that will work. That's not the idea, I think. No, the storage locations, it is in empty gas, oil fields, saline fields, underground mineralized areas. There's plenty of storage capacity. That's not a problem at all. Once again, the big advantage of direct air capture is that where that facility is, we can also capture the CO2. Yeah. There have been plenty of calculations about this, and by the time we reach that limit, I think we're in good shape. Yeah.
How big is, maybe, I'm not sure if you're alluding to this, but how big is the reach of, like, say, like one of the towers? Like, how big of an area does that cover?
Okay. Yeah. I think it's in the previous. This tower, you mean? Yeah. This is an artist impression. I can tell you one thing. This is not how our machine is going to look like in the end. And probably it's also not the place where we're going to put it. Yeah, because we can put it anywhere we want. So why should we put it in a field? But But anyway, it's just people always ask this question, okay, how does this look like? How will this work? And you have to think about this 100-ton machine, 100-ton CO2 per year capacity. Currently, in our dimensioning, you think about let's say a pallet-sized machine, which is roughly 2 to 3 meters high. So these are units, and we make actually modules which you can stack, and so you can build up capacity in a modular way. Of course, you can stack them, you can place them relatively close together. Of course, you have to suck in a lot of air, so you need to have space for that. But we also often make a comparison with, for example, trees. People ask, if we plant trees, why don't we do that? And by the way, that's a very good idea to do. First of all, we should stop killing forests. That would be nice to start with. But we made a calculation. These are all my backup slides, but I'm not going to bother you with that. But maybe this is nice for comparison, just to see what the footprint of it does. So an average, a grown-up tree can capture like 25 to 30 kilograms of CO2 per year. The bad thing about trees is that they tend to die after a certain time, and then they release a lot of this CO2 again. So it's not what they capture is not always what is stored away permanently. So you have to find a way to store it away permanently. But anyway, assuming all this, we made a calculation. This was for a presentation for an American audience. Like the USA aviation industry emits 200 megatons, so that's million tons of CO2 every year. By the way, we think that's a lot, but aviation emits roughly only 2% of all emissions. And if you would have to compensate that with a forest, you would have to make a forest the size of the state of California. And I can tell you, California is a big state. So that's a lot. And with our machines, these towers that you saw, we can cover that up with 15 baseball fields of equipment. So our footprint is much smaller than that of forest. But that's a comparison with forest, and we're not saying that we shouldn't do forestry. Of course we should. But that's also one of the disadvantages of forestry. It will not be enough. If we would plant all available area on Earth with trees, that would not even be enough to cover the problem, let alone what it do with biodiversity and available places to grow crops, etc. So, yeah.
I have 2 questions.
Yeah, please.
4 questions.
Yeah.
First, Marco, thanks for the presentation. Very nice.
Thank you. Was that a question?
No, it was a compliment.
Thank you.
A compliment, 2 questions.
Okay.
First, I was wondering if while you managed to reduce the cost of your prototype, if you're targeting special cities or country, because I can imagine that if you put 10 of your columns in Eindhoven or 10 of your columns in New Delhi, so you will get out much more CO2 in New Delhi, so you can manage to sell much more CO2 per column in comparison to Eindhoven. So
Why would that be? Sorry, I don't read it.
It's a much more polluted city, so it will be much more polluted air coming into a single column out of a cleaner city.
I don't think that really makes a big difference. Yes, there are systems to capture CO2 from what we call point sources, so like industry plants, energy plants. Of course, what comes out of the chimney there has a really high CO2 concentration, so yes, it's a good idea to capture that. And that's specialized equipment. That's also something that we're not going to pursue. It's by the way, it's not that negative. We are capturing CO2 from ambient air, and the CO2 concentration worldwide is almost the same everywhere. And yes, maybe in city areas it might be a bit higher, but it will not be twice as high. So it's dispersed evenly in the atmosphere. Yeah. So is that question to your answer? Yeah.
The other question is, so the air that you are putting back in the atmosphere, that will be CO2 free, or?
Yeah, of course, it will not be CO2 free. The question is if the air, sorry, I interrupted you. Was that your question?
I was also wondering if the pollutant like particle matters, etc., stays in the filter or that goes back out.
Okay, yeah. So the question is if the air that comes out is free of CO2, and if we have pollution which is in the air, if it stays in the filter or if it will also come out. Yeah. The answer to the first question is the air that comes out will not be entirely CO2 free, because we will not be able to catch 100% of the CO2. Of course we would like to, but that will probably not be the case. But it will be with a way lower concentration of CO2. That's one question. Yes, there is pollution in the air everywhere in the world, actually. By the way, one of the biggest polluters that we face is actually water vapor. But that's a different story. But for example, dust. Yes, of course we have to filter the air before it enters into our machine. Yeah. And actually that's one of the areas that we are actually investigating further during the next year. But there are systems available to, let's say, filter air from certain dimensions of polluters. That's possible. And we have to, of course, we still have to investigate how that will actually affect our performance, and maybe how it will deteriorate it. That's also possible, yeah. So I don't have a final answer on that one yet, yeah. And we're happy with some help from Tino there. Thank you. Yes, please.
So, just going on with this question, so the film you're using to capture the CO2, is it durable, like it can sustain for like 30 years?
Oh yeah, I forgot to say, I brought a piece.
Or it gets polluted slowly and slowly, so you have to change it?
Yeah, there's two things. It's I can give it a it's a piece of cloth, actually. It looks like my shirt, but we could even make clothes that capture CO2. But I wonder how to get it out still. But that's a piece of cloth. It's this is not the one we are currently using. It's not as porous as we currently use, but it is quite strong, as you can see. It is made of carbon fibers. This type of material is commercially available. It's used for filter masks and that kind of stuff. You will also find it in your vacuum cleaner and that kind of stuff. So it is widely available, but we modify it in a certain way. And yes, of course, any material will deteriorate in due time. But regarding, for example, dust particles or other polluters, we have to, when we take off the CO2, when we release the CO2 again, we heat up the material a little bit. But then we also have to what we call strip it off. So we have to blow it out of the material. So with blowing the CO2 out of the material, we can also strip off any polluters. That's the current idea. Yeah. Yeah. One more question.
What do you use to blow it off? Because you need some gas.
CO2.
CO2.
Yeah. 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 If we would blow in air again, that would be a waste of effort. Yeah. Yeah. But these are quite puzzling questions. At least they have been. Yeah. Yeah. Thank you. Thank you. Yeah. Any more?
How exciting is to be in this venture?
Sorry?
How exciting is to be in this?
How exciting it is to be in this venture? No, it's really boring. I shouldn't have done. No, it's really exciting. It's in several ways it is exciting because yeah, it is about something that really matters. I think that's the most exciting thing. If this would be about some kind of commercial product that we would sell and that would be consumed and that's it, and we would make nice profits, that would not be exciting, for me at least. So this is about one of the biggest challenges of our time. That makes it really super exciting. That's also what we notice from people who engage with us. They ranging from students to scientists to politicians. Everybody gets excited about this topic. So that's also in our advantage, of course. It is exciting because it is technically it's a huge challenge. So we have, let me say, we have had our ups and downs, and we will still have ups and downs. And we have ups, and then we celebrate, and the next day we are, oh my God, what is this? But still, we're still alive. That's the good news, and it also makes you stronger in the belief to actually achieve it. What makes it super exciting is that we have a team of which is science heavy, as I told you, and but the team spirit is really good because we all pursue the same goal, and everybody believes in it. So everybody in our team is not in there for the money, or there is no money, but just to do good, or okay, you know what I mean. It is exciting because it is, although we have a very, let's say, favorable topic, it is still hard to get enough funding fast here in the Netherlands. So now we can still make progress with relatively small amounts of money, but if we go to our next prototype, and certainly if we are going to do pilots, certainly if we are going on the market and if we really have to scale up, there's going to be a huge funding needed for that. And this early starting phase in which we are in, where there's really high risk, but possibly also high return, it's quite a difficult phase to be in to get funding. But so far, knock on wood, I would say. And it's also difficult, and then I will stop. I still have a lot other exciting stuff to tell. It's also difficult to for people to understand that this is a deep technology, as we call it. So the research that we are doing is quite fundamental, I always compare it with people who say, I have a startup, and what do you do? I make an app or something. You can do that overnight. This takes years to develop, and then still it is really challenging. So this fundamental research aspect that is connected to this is on one hand challenging. On the other hand, for us it's also a motivator, because we always say, if it would have been easy, someone else would have already done it. So that it's also in some way motivating that we didn't find any way yet that this will not work. And yes, it is difficult, but it also shows, and also literature that we read, that, let's say, the solution that we choose has not been done before yet. Yeah. Marco is having some non-verbal communication.
Well,
to my
I mean, if there's no more questions, then I
will be here for a few drinks. And,
exactly. Thank you, Marco, once again.
It was a pleasure.
Thank you very much. And for everyone here, first, the people that are watching, thank you for watching. We are going to go have a drink. We hope that you are here another time in real life. You're very welcome to. For the people here in the room, we can go have a drink in the bar. It's also a possibility to stay for dinner. Were you staying for dinner as well?
Well, if you ask.
You can have a bite to eat. It's on the house for you. So, but you're also very welcome to join. There's an Innovation Café special. I'll come up to you and check. I need to check with the kitchen first what it is, but I'll come and ask if you want to join us as well. But I hope to see you in the bar for a drink. If you did bring a glass, please bring it with you back, and then we hope to see you again next week. So thanks. Okay.
Thank you. Merci.